Hey everybody, Dr. Retzek here with you. This is our first video in the final section of Calc 4. This is section 16.4 on Green's theorem. Let's get started. So what we have here is a picture that I've already drawn for us, and we got to make sure we're at peace with all the components of this diagram. First of all, section 16.4 is happening exclusively in the xy plane. These are all two-dimensional pictures. Those light gray arrows are some vector field in the xy plane. So at every point x comma y, there is some arrow. The vector field in this discussion is C1. Remember, all that means is the first partial derivatives of both components of the vector field f are continuous. And then I and j, those stand for our classic old unit vectors in the xy plane. So I is the vector 1 over none up, and j is the vector none over 1 up. Now, we have this little blue rectangle, which you're imagining has its bottom left corner at location x comma y, and it's tiny. It's delta x by delta y. So this is one little tiny piece of a very fine grid that's happening in the xy plane. Okay. There are two notions that we're trying to develop today. We're not even going to state Green's theorem today. We're just trying to figure out two different physical notions that go with this diagram. For the purposes of physical intuition, your book thinks of this vector field as maybe like a velocity field for a fluid. Like imagine a very thin layer of water coursing across a two-dimensional plane. And I think we'll adopt that visualization ourselves from time to time in today's discussion. Okay, here's the first physical thing that we're interested in. Loosely, we're interested in, well, how much water is leaving this rectangle? And you can see some of the gray arrows appear to be pointing into the rectangle, and some of the gray arrows appear to be genuinely exiting the rectangle. And we want sort of the net effect. So the way we're going to keep track of that net exiting of the rectangle is by thinking about a bunch of arrows representing exit from the sides of the rectangle. Now, along that bottom edge, it's clear those rectangles are not even exiting, they're entering. And so they're going to contribute a negative amount, as will the gray arrows along the left edge of the blue rectangle. They'll contribute a negative amount. But the gray arrows along the top and right edge of the blue rectangle will contribute a positive amount. And then on balance, we'll have some measure of how much the water is coming into the rectangle versus how much the water is leaving the rectangle. So that's our plan. To execute this plan, focus your attention on the bottom edge. In particular, like let's say we were interested in that vector right there. So that's f. You can see that f has two components. There's the part perpendicular to the edge in question, and there's the part along the edge in question. The red arrow will interest us later. Right now, it's the green arrow that interests us, and we want it to count negatively because it's not leaving the rectangle, it's entering. Okay, so here's what we're going to do. Let's look at how much of the black arrow F is perpendicular to the edge. And if F at any given point has components, traditionally we use M depending on X and Y in the first entry, and N depending on X and Y in the second entry. If F looks like that, then let's compute F dot, okay, now think about the arrow exiting that bottom edge. So that thick red arrow exiting the bottom edge. That, what is that? That's none over 1 down. That's negative j. So that's the scalar amount of that green arrow in our picture. F dot negative j. Okay, fantastic. Now, that's happening at each point along the bottom edge. So the grand total across the bottom edge we're going to take those scalar amounts and we're going to multiply by delta x to capture how much of all the different black arrows are pointing in versus pointing out along that bottom edge. So we're going to take this quantity, F dot negative j and we're going to multiply by delta x. Now, this seems a little unfair because it's just not true that the black arrow is the same at every spot along the bottom edge. I mean, this black arrow here is a little longer, but maybe has exactly the same green contribution. This black arrow here is way shorter and has a totally different green contribution. So we put quotes around this in the sense that, well, wait a sec, doesn't this depend on where we are along the bottom edge? So here's what we're going to do. Let's just take this one here, F specifically at xy, use its green contribution, and just say, well, I'm sure they're all roughly that. After all, the rectangle is tiny. After all, the vector field is C1. How different can the black arrows be across all those different locations on the bottom edge? So we elect to do F specifically at xy, dotted with negative j, and then multiplied all the way across that bottom edge. And what is that quantity? That's, let's see, remember what j is, so that's negative n at xy times delta x. Okay, so that is what we're using as the contribution of the vector field leaving the bottom edge. And on our picture, it looks like that's going to come out negative for sure. Okay, great. We want to do this on all the other edges. So Let's go to right edge next. Okay, same story, only for the right edge, is it okay if we use that vector as representative of all the vectors all along that right edge? If it's okay, then look at its green component perpendicular to the edge in question. To pick up that green component, I think we should do black arrow dot I, 1 over 0 up. So let's do black arrow at, what is that point where that black arrow is? X plus delta x comma y. And then let's do dot I, and then let's multiply by the entire length of that edge, which is delta y. So I think we got m at x plus delta x comma y, all times delta y. Okay, perfect. All right, we want to do this for the other two edges now. Let's see if we can do it quickly. All right, here we go. Let's do top edge next. Top next. All right, for top, maybe can we use this arrow here? Let's use that one. Let's use that representative of our vector field along that top edge. Okay, so let's find all of its green contributions across that top edge. Okay, here we go. So that's f at, what is that point? That's x over y plus delta y up, dotted with, okay, out that top edge, that's dotting with, what direction is that? Out the top edge is 0 over 1 up, so that's j. And then let's multiply that by the entire width across the top edge, so not delta y, delta x. And so what do we got here? That's n x comma y plus delta y, all times delta x. And finally, left edge, full circle, if you will. Okay, left edge, one more time back to the picture. Why don't we use this one again? Let's use this one, the one located in the bottom left corner, as representative for that left edge. You know, we could use the one from the top left corner or the one from the bottom right corner. Electing to use this one in the bottom left corner as representative of what's happening along the left edge gives us the nicest formulation of this idea. So it's just a choice, but don't think we had to. Okay, here we go. Left edge. So that was f at good old xy. And then we want the part of that leaving the left edge. And in our picture, it looks like they're all going in. So this is going to be some sort of negative contribution, but we should definitely be dotting with negative I. That's 1 left, none up. And then that is over the full extent of that left edge, which was delta y wide. So what do we got here? Negative m at xy delta y. Okay, so we have these 4 contributions. We'd like to group them top, bottom, and left, right. So we're going to group these like this. Take those two together, and then take these two together. All right, let's do the orange ones first. If we add the two orange pieces together, look what we have. Adding the oranges, we have, so grand total. So this is over all the edges now. Grand total. Well, you got right plus left. So that's m x plus delta x comma y minus m right at xy all times delta y plus, and now let's do the purple. Purple is n at x comma y plus delta y. Take away, n right at xy. And that was all along a width of delta x. So that's our grand total. And again, we're just measuring components of the vectors from our vector field that are exiting the rectangle. And we've done all four sides, and that's the grand total. Now, check this out. In those first brackets, let's go like this to make this thing look like a familiar object. Let's divide what's in the brackets by delta x and then pay on the outside. Plus, and then on the other term, let's take what's inside the brackets and divide by, you guessed it, delta y. And then pay on the outside. Okay. Now, when delta x and delta y are tiny, in other words, when that rectangle is super tiny, look what we have. In these first brackets here, these, is that not roughly the partial dm dx? I mean, look, it's rise over run where the x variable changes and the y variable is fixed. So in a chapter 14 way, that's pretty much dm dx. So we have our grand total is now pretty much dm dx, delta x, delta y plus, and then likewise, look at that grand total. In the second brackets, well, that's rise over run for n, where y changed and x didn't. So that looks like n's y partial. Okay. So that is our grand total. And the definition of that quantity right there, that's called actually the flux across the boundary. All this is called flux across boundary. And if you divide by the size of the rectangle, if you divide the flux across the boundary by the size of the rectangle, which is delta x, delta y, that's just the area of R. This is just the area of the rectangle. If you divide the flux across the boundary by the area of the rectangle, you get something that we call the flux density. So this long derivation is just to arrive at this statement. The flux density is nothing other than dm dx plus dn dy. Now, flux density, I think that's terminology that maybe a physicist or an engineer would use. The math word for this quantity, the flux density, is in this definition. Definition. The divergence of the vector field F depending on x and y, with first component m depending on x and y, second component n depending on x and y. So divergence is the word we're defining. It's the sum of the partials, dm dx plus dn dy. Now, this whole discussion could have just started with me writing this definition down. And you guys would have all nodded and said, okay, cool, divergence, new vocab. I can remember that. dm dx plus dn dy. Got it, boss. But the fact that we went through it and it's related to the picture gives us some added intuition about what divergence is. So consider this example. If you had a vector field like this, say you had that vector field and you imagine superimposed on there the little blue rectangle. Well, you tell me, more coming in or more leaving? Does it not look like the arrows entering the blue rectangle are bigger than the arrows, quote, leaving the blue rectangle? It does to me. And so that means on this picture, I'm expecting the divergence that's our symbol for the divergence of a vector field. I'm expecting the divergence to come out negative. At that point right there, it looks like the flow is compressing. This is like when you're going along just fine on the freeway and then there's some traffic up ahead. Everything compresses. And then you make it through and then everything diverges. So in that picture, my guess is because the arrows entering the blue rectangle are bigger than the arrows leaving the blue rectangle, that the divergence is negative. If it had been the other way around, then I would have guessed that the divergence was positive. If the arrows had all been the same length, then I would have guessed the divergence was 0. All right. So divergence is somehow measuring compression. If it's negative, you're compressing. If it's positive, that's the dog. Hey, sorry for that interruption. The dog is a psychotic. So now we know about divergence. You guys are reading about the exact same discussion, about the exact same drawing, except what is of interest to us now is not the flow across the boundary, but rather the flow along the boundary. So the thick arrows look like this now. If you rederive all of that, except your interest is the part of the vector field that is along the boundary rather than perpendicular to it, you get a whole different physical quantity called the circulation. So you guys will read about that. Come to class with questions. I'll see you next time.